said we were starting at 2:05, it's 2:06.
I'm sorry, okay, yeah, that's right. It is 2:06. We're going to get started in just a few seconds. So this afternoon we're going to have some dev updates from the 3 different teams that have actually started doing experiments and coding with the Beam chain. And then we're going to have 2 roundtables, one on signature aggregation and the other one on reducing the slot duration. Our first speaker here is Gajinder from Zeam, and I have a special trophy for him for making it today, which is the VDF.
Whoa!
So there's only 100 of those that have been manufactured. This is a 1 of 100 NFT. And it works. It probably won't be used in production, but it works.
It's like Zeam.
Okay, the floor is yours.
But soon, hopefully soon, we'll be running in production as well. Cool. Thanks, Justin, and very excited to be here. Great energy, and let's get into it. So I'll talk a little bit about Zeam, and since Justin unveiled the ZK Rails for Ethereum Consensus Vision at DEF CON, we have been on a mission, and then we'll talk about phase 1 of that mission and one of the outcomes of that mission, which is Zeam multi-prover. And the 4th point is that we'll also talk about proving with 3SF, because 3SF is something that we integrated into our STF function, and then we'll make a very juicy announcement, hopefully. So, all right, so the purpose of Zeam existence is that we wanted to develop a Zig Lean client, Beam client, from the first principles itself, because we felt that Zig was a language which is highly performant and very versatile to build the target builds, target guest programs that can be proven on ZK VMs, and so that was one of the big motivation. And all of our work, you can find us on the BlockBlaze organization, and the Zeam work particularly at BlockBlaze/Zeam. And while me and Guillaume are the primary leads of this project, we have a very vibrant contributor community that is emerging. And so let's talk about what we have been doing. So our mission for 2025 is to build a proof of concept to demonstrate the ZK Rails in action, and for that we have integrated ZK VMs, at least one, and we are working on many others. And while doing that, we will be building various libraries that are relevant to ZK ecosystem and Ethereum community, so that by end of the year, when Beam specs are released, we are Beam ready. And our mission is divided into 2 phases. And so let's look into what we have done in the phase 1, which is the first 6 months of 2025. So phase 1, so there are 4 pillars to phase 1, and one of them, so these pillars are building the building blocks and libraries, doing state transition, function proving, and then basically building up the Zeam client, which does end-to-end proving as a DevNet. And the last pillar is community. So on building blocks, we have implemented SSZ, which is extendable, and we basically aim to extend it with Poseidon 2 now. We are doing optimizations on it, but that is not really the focus, because first we want to demonstrate the basic concepts. On P2P layer, we have done some P2P glue, but there is a lot to be done over here, especially with the P2P networking research that is ongoing, and when we will have more clarity on it, then we'll see how we can contribute to it. But for now, we will just use what Ethereum researchers are going to churn out over here, and by using ZIG bindings on it. So in our estimation, this is 80% done for phase 1. And then on state transition proving, we have achieved proving and verification with risk 0. And so basically, so you need to have state transition function, but we went beyond a basic state transition function and pulled from our phase 2 goal and translated 3SF, Vitalik's 3SF, Mini 3SF into our state transition, and we'll talk about it later. And so we also did quite a work on Powder, which we are now denoting with OpenVM, but there is still some work. This work needs to be restarted with Powder dropping its support for ZKVM, and Guillaume mentioned about this in his morning presentation. So for our phase 1 goal, it was to basically at least have one ZKVM proving, so that is done. But yes, we are focused to get other ZKVMs working as well. And for the client, which is the third pillar, we have developed various modules, and most notable of them is fork choice, which is now 3SF fork choice, again translated from Vitalik's work. And then one of the core modules is Proving Manager, which we'll also talk about a little bit later. And now the goal, there are two things that are pending for now, which we are focused to get it out, which is having a multi-node in-process DevNet, where basically the chains are building out on basis of 3SF state transition function, and then the next step would be to make it a multi-node by having integration with the Rust P2P. So again, we think that we are 80% done over here. And the last bit is community, and we are having active weekly calls. We have active Telegram and X group, and we have contributors that are working on various initiatives like Zighash, Zigli P2P, and having Poseidon to integrate it with our SSD. But but we are trying to make sure that we can get focused outcomes here as well. And we want to collaborate with EPF on that and start some initiatives there as well. So here, again, we are like 80% done. So outcomes of this are intended to be a multi-node DevNet and basically have multi-ZK proving, multi-proving with different ZKVMs, and then we want to basically also integrate Poseidon 2 into our SSD and sort of demonstrate how it will work, and maybe also then do some benchmarking on it. But as Guillaume mentioned in the morning, benchmarking is not that much of a concern right now because we are focused towards getting the functionality working first. And we think that we'll be able to do it by end of July. So let's look into one of the outcomes of our work, which is the multi-prover. And this is something that you have already seen, but again to reiterate, we have a basic client which basically needs to interact with ZKVMs and run the runtime, produce proof, and sort of verify it. And for that, basically you need to give it state input, you need to give it block that you want to prove, and then the proof will be generated, which will be transmitted over the network, and the receiving nodes will also receive the state diff and basically verify that in ZKVMs, and basically then they will be able to even attest to the network. again, going a little bit deeper into it, let's look into the anatomy of the guest program. So you have 3 components for it, which makes a guest program. There is an instruction set on which ZKVMs, or you can think of that, circuits are based, the proving circuits are based, and then there are proof systems, and then the third is the runtimes, which is the state transition functions that various third-party suppliers will provide to a client, or the client itself can come up with. So we have quite a good diversity over the instruction sets, and major being RISC-V, and if you look at e-proofs, you will also see MIPS in action. So other instruction sets are EVM, Petra, Cairo, Maiden, and all of them they are different ZKVMs who are targeting these instruction sets. On proof systems, you have Binias and Plonky 3 as the viable proof systems, but it seems that Binias needs some more work to make it performant, so most of the proof systems are Plonky 3, but we also are seeing some custom backends that ZKVMs are developing, like SP1 Hypercube. And then you have the runtime providers, which most of the ZKVMs might provide a default runtime, and then you will have players like Zeam coming into the picture and providing the runtimes to various clients to do the proving and verification. So now let's look at how Zeam multi-proving actually happens. So you have a guest program, and but it's basically not just a guest program, it's made up of a runtime, which basically for us is RISC-V code that is compiled, and that RISC-V code is basically state transition function that we have written and with some runtime glue, but it also needs an invocation glue which is to work with that particular ZKVM. So this is where multi-proving comes in, and this is where games work comes in, which he mentioned in the morning, that it conceptually it's simple, but you have to figure out how to hook it all up to make it work. And then in Zeam you have, for example, multiple different guest programs, and you have multiple different ZKVMs that are out there. And they are all coordinated by something we call Proving Manager. And so that Proving Manager takes a pre-state, it takes a block, and it takes proving ops, and then basically it selects, or it can do a multi-selection as well. It selects whatever ZKVM you want to prove on, and then picks that particular runtime, generates the execution trace, commits, and then gives you proof, and something that again you can run back onto the verification chain like this. So as you can see over here, this is our manager, which basically takes the state, block, and proving ops, and what it does is basically serializes that input that it receives and sort of provides it to the invocation glue, which then loads that to the ZKVM. And so this is, and that invocation glue then starts up the runtime in the ZKVM itself, and the runtime receives that inputs from ZKVM, it deserializes it, and then it runs the state transition function, and then you have then you basically commit to the output, and you have proofs. So here you replace this OpenVM with Powder, but this is essentially what you saw earlier as well. So we have achieved proving and verification with Z0, and now our task is to move to the next one. We did devote a lot of work to Powder, but it has basically gone down our priority list, and most probably we'll either be doing picking up with SP1 or with ZISC. And coming to the second part, which is the state transition function. So what we did was we pulled from our phase 2 goals, and we decided that, okay, this looks, 3SF looks quite exciting. So we translated Vitalik's mini 3SF into Zeam, and for that basically we came up with SSZ containers for that, and then translated the state transition function as well as implemented the fork choice. So the containers for SSZ containers for 3SF look something like there is a checkpoint to which there is no epoch now, so there is root and a slot. And then there is a vote. Vote is on a head, target, and sorts, and all of them are basically the slot root checkpoints. And you have we have block body where basically you have a series of these votes. They are not aggregated as of now. And then you have state where you track latest justified, latest finalized, and what routes are being justified and who is justifying them. So the routes that have not yet been justified but are in contention, are candidates for justification. And then then we have an apply transition. This is our apply transition function, which is just like how you do it in beacon consensus. You have process slots. Basically, you roll the state to the current slot, and then you process the block. And in process block, basically you make sure that you process the block header, the block's parent matches with what state's last block header is. So you do that to make sure that you establish that this is a chain, and then you do process operations, which is where we apply the votes. And in the end, basically you verify that that the state root that you get is same as the root that is in the block, and that basically sorts of validates your state transition function. So looking at how we apply the votes, there is a bit of difference from Vitalik's implementation, because his implementation is about starting the slot, the Genesis slot at slot 1. So this is something that we did, that we start the slot, keep the Genesis slot at slot 0, and this is some of the modifications that we did, and that is the other work that we translated. And basically we wrote up some scenarios to prove, and that is something that you can just go to Zeam repo and execute, and it will do this particular scenario proving for you. So coming back to our mission, we are 85% complete on phase 1 and a little bit on phase 2 as well. But we are here to make an exciting announcement that with all the incredible acceleration that has happened in the ZKVM space, we have sort of updated our target to a more ambitious one. And we'll basically do EL integration, which is okay. I mean, it's not really that ambitious, but we will also implement delayed execution to it, because we want to do full block proving with EL and CL. And this is, and with that, we want to prove that we want to demonstrate how lean clients will work without EL, because the receiving client will not have any EL attached to it and will be able to attach to the network without having any EL. Yeah, that's all.
Thank you, Gajendra. I didn't realize that you were doing this big announcement. Any questions for Gajendra?
I'm just curious, have you benchmarked any of the proofs yet? Like, how big are they?
So all that is happening at heap proofs. I think so that work is pretty cut out for that. We will benchmark our state transition functions.
Any other questions? Okay, thank you so much, Gavin.
Thank you.